Hello students, in our previous classes we saw that normal shift, and I derived the formula normal shift is equal to T bracket 1 minus 1 by mu, where mu is the refractive index of the medium. From this expression we see that the normal shift increases with the decrease of refractive index. So, where T is the thickness of T is the actual depth. See the figure, here we have a water is acting as a denser medium. The actual depth of water is named here as T, and the object appears somewhere at different location from its actual position, and that depth is named to be as D. So, the difference between T and D, that is the difference between normal depth, that is actual depth, and the apparent depth is said to be as normal shift. It depends upon the actual depth as well as the refractive index of the medium. Now, we will see the factors on which the refractive index depends. Already we saw that the refractive index depends upon the speed of light, wavelength as well as the nature of the medium. Here we are saying that with the rise of temperature, when the temperature increases, molecules move apart. As the result of that, the rareness of the medium increases. As the rareness of the medium increases, the refractive index decreases. So, ultimately we can say that with the rise of temperature, the refractive index of the medium decreases. Now, we will see some of the examples related to normal shift. Examples of normal shift. First, here a fisherman who is in the rarer medium, if watching the fish appears to be somewhere different location than its actual location, or if any corals or any sea creatures are there, and if that objects are absorbed by a person from the rarer medium, then it appears that the objects which are present in the denser medium as up of the surface than its actual location. Let us see that. Here we have, say suppose that sea is there, sea is denser medium. Here say suppose that some corals are there. These corals, if viewed by a person in the rarer medium, the beam which arises from the object in the denser medium moves away from the normal as it enters into the rarer medium. So, it will goes like that. If a person is watching this, say suppose that eye of the person have the line of sight at somewhere like this. So, here the actual position of the object for the person who is in the rarer medium appears to be somewhere different location than in its actual location. This is the actual location, and this one is apparent location. So, the object appears to be somewhere different location for the person who is seeing in the rarer medium. So, this is one of the example of normal shift, which is actually an optical illusion. Another example is if a fish sees the person in the rarer medium, how it will be. Let us see. Here we have interface. Suppose that this is denser medium, normally it is considered to be as sea, water contains. Here a fish is there. So, this fish is viewed by a person from the rarer medium. If fish is viewing the person who is standing in the rarer medium, let us suppose that here we have a person, the beam which arises from the rarer medium, or suppose that fish is seeing the person in the rarer medium. So, the beam which comes from the rarer medium move up to like this. Here it will make an angle of incidence I, and after entering into the denser medium, the beam bends towards the normal, making an angle R. For the fish, the line of sight is this one. So, for fish, the person appears to be somewhat taller than its actual height. So, when the person is in the denser medium, and if he is watching the object in the rarer medium, then that rarer medium, the object appears, the object which is present in the rarer medium appears to be somewhere taller than the actual size, like what we are seeing in this case. Fish is seeing the person. Fisherman is standing in the rarer medium. If we assume that the actual height of the person is h, the beam which comes from this person from the rarer medium, when it enters into the denser medium, it bends towards the normal. As a result of that, the line of sight for this fish will be this line, which appears to be as somewhere different locations. So, the height of the person appears to be taller than his actual height. So, these are the examples related to normal shift. Next, we will see the total internal reflections. Here, the definition of total internal reflection says that it is the phenomenon in which a beam of a light that arises from the object in the denser medium when it enters into the rarer medium, if the angle of incidence is more than the critical angle of incidence, the beam of a light which enters from the denser medium reflects back into the same medium. So, it is the phenomenon in which a beam of a light which arises from the object in the denser medium reflects back into the same denser medium for an angle of incidence greater than critical angle of incidence. Here we have three diagrams. Let us try to understand, and let us see the various steps involved in it. Here, in first case, we have angle of incidence I and angle of refraction R. As the beam is entering from denser to rarer medium, it will bend away from the normal. In the second case, angle of incidence has been increased. When it increases, angle of refraction will also increases and the beam will move little away from the normal. In third case, at a particular angle which is said to be as critical angle, the refracted beam grazes over the surface such that angle of refraction R is equal to 90 degree. If the angle of incidence is more than, critical angle, then the beam reflects back into the same medium. So, this phenomenon where the beam which strikes at the interface, instead of getting into the other medium, reflects back into the same medium, this phenomenon is said to be as total internal reflection. Now, we will see the condition related to total internal reflection. First one, object should lie in denser medium. Second, angle of incidence must be greater than critical angle of incidence. So, critical angle of incidence is that angle at which the refracted beam grazes over the surface. So, this is the definition of a critical angle. Now, we will try to relate the critical angle as well as the refractive index of the medium. So, from the diagram number 3, using Snell's law, we get sin IC divided by sin R is equal to refractive index of rarer medium with respect to denser medium. Now, here the value of R is equal to 90 degree. After putting that value, you will get sin IC divided by sin 90 is equal to refractive index of rarer medium with respect to denser medium. We know that sin 90 is equal to 1. This expression gives sin IC is equal to refractive index of rarer medium with respect to denser medium. Now, using the principle of reversibility, you can write refractive index of rarer medium with respect to denser medium as equal to 1 divided by refractive index of denser medium with respect to rarer medium. So, sin IC can be written as sin IC is equal to 1 divided by refractive index of denser medium with respect to rarer medium. So, this is the formula for the determination of critical angle of incidence. If we know the refractive index of medium, then critical angle of incidence can be determined. For example, for glass, refractive index of glass with respect to air is 1.5. Now, critical angle of incidence for glass is sin IC is equal to 1 divided by 1.5, or this can be written as 2 divided by 3, or it is 0.66, which is approximately equal to IC equal to sin inverse 0.66, which gives approximately 42 degree. So, for the case of glass, at an angle of incidence of 42 degree, if the angle of incidence is more than 42 degree, then total internal reflection can takes place. So, these are the conditions that is required in order to have the total internal reflection. First one, the object should lie in the denser medium. Second, the angle of incidence must be greater than the critical angle. Now, we will see some of the examples related to total internal reflection. There are few examples related to total internal reflection. First one, mirage effect. Second is looming. Third one, total reflecting prisms, the prisms which works on the principle of total internal reflection. Third one is brilliance or sparkling of a diamond. Fourth one, the optical fibers. Let us see first the mirage effect. Here, sometime man see a false perception of presence of stagnant water or a pond in the sandy region during hot summer due to the appearance of image of a tree is called mirage effect. So, it actually gives false perception that nothing is there in this place, but a person will realizes that there is an image of the tree. As a result of that, person perceives that some pond of water or stagnated water is there at this point. So, this is due to the total internal reflection. Let us see how it actually happens. Here, during the summer season, the lower surface of the earth is hotter than the upper surface. As a result of that, the molecules of the lower surface move apart and temperature will be more. Because of that temperature, the surface's medium becomes rarer and its refractive index is low. As we move into the upper layers, the absorption of the temperature is low. As a result of that, the molecules do not move apart. As a result of that, comparatively, the medium becomes denser. So, the denseness increases as we move away from the lower surface to upper surface. In this way, we will get two requirements, that is a denser medium as well as rarer medium. Now, according to the total internal reflection, the object should lie in the denser medium. Here, if any tree is there in the denser medium, the beam which comes from the tree undergoes refraction. When it enters at the first layer, it will move away because the medium is rarer than the upper layer comparatively, and when it enters into the second layer, again it moves gradually, it moves away. At some point, when the angle of incidence is equal to critical angle, the beam moves or grazes over the surface. If the angle of incidence is more than that critical angle, then instead of getting into the second medium, it will move back into the same denser medium. For a person, line of sight will be like this. He will see the presence of image according to his line of sight, which appears to be at this point just opposite to the actual position of the tree, which seems to be as an image of the object. This gives false illusion to a person. So, this effect is said to be as mirage effect, and it is totally depends upon the total internal reflection. So, conditions here is that angle of incidence must satisfy according to the condition of total internal reflection, that is the angle of incidence must be greater than the critical angle of incidence. Under that condition only the total internal reflection can be seen. So, the mirage effect normally seen in sandy region where the temperature is very higher. Next we have the looming. Normally looming is seen icy areas where ice is there. Suppose that here we have icy region, say that in iceberg a ship is there. So, here because of icy region temperature is low, lower temperature means the medium is denser. As we move upper side, temperature will be more than the denser medium. As a result of that, the medium becomes rarer, and if the ray of light moving from the ship, it will undergoes refraction at several layers. Now, at first layer it is moving from the denser to rarer medium. So, it will bend away from the normal because the medium is rarer, and then when it strikes at the second surface, the medium is further becomes rarer. So, as a result of that, it again deviates from the normal at some distance, and after some time it will move normal to the surface, and again it will reflects back into the same denser medium. If a person is standing in the denser medium, for his line of sight, he will see the image of the ship somewhere here, which appears to be an inverted image of the ship. So, here he will see an inverted image of the ship which is present in the IC region. This effect is said to be as looming. So, looming is again depends upon the total internal reflection. It is based on the principle of total internal reflection. Next, we will see the brilliance or sparkling of diamond. Here the refractive index of diamond is 2.4, which introduces critical angle as 24 degree or more or less 24 or 23 degree. So, if the angle of incidence is greater than this 24 degree, then total internal reflection takes place. So, if diamond consists of several faces, because of angle of incidence, a critical angle of incidence 24 degree, several faces can be cut in order to have many total internal reflection by the gemologist. Here, if a beam of light enters from any one of the surface, if it satisfies the condition of angle of incidence greater than critical angle, then this beam undergoes, it will strikes at the other surface. If the angle of incidence is greater than critical angle, then it will reflects back into the same medium. Again here, if it satisfies the condition of total internal reflection, it will reflects and multiple reflection will takes place within the diamond. As a result of that, there will be a sparkling of the diamond or brilliance of the diamond can be seen. It is also again based on the total internal reflection. Next, we will try to see the total reflecting prisms. Now, we will see the working of prism, which is based on the total internal reflection. Here we have a right angle, isosceles right angle prism, whose two angles are 45 degrees and one of the angle is 90 degree. Now, the refractive index of glass is mu is equal to 1.5. We have to find out the critical angle in order to check whether the total internal reflection will take place or not. According to the definition of total internal reflection, and the formula is sin I C is equal to 1 by mu. Here sin I C equal to 1 by 1.5, which gives approximately I C is equal to 42 degree. Now, if the angle of incidence if 42 degree, then there is a possibility of total internal reflection. Now, the beam is entering and it faces the first surface of a right triangular prism. At first surface, it is moving normally, therefore, Snell's law is not applicable. The beam will strikes at point P, let us say. Here at point P, if the angle of incidence is more than critical angle IC, then beam will reflects back into the same denser medium, otherwise it will move into the rarer medium. Now, let us check the incidence angle, whether it is 42 degree or whatever it is. Look at the triangle PQR. In this triangle, angle Q is 45 degree, angle R is 90 degree, therefore, QPR will also be equal to 45 degree. Now, the line XY is acting as a normal, therefore, the total sum of this 45 degree and the angle RPX is also equal to 90 degree, therefore, RPX gives 45 degree. So, here the angle of incidence in our case is appears to be 45 degree, which is more than the critical angle 42 degree, therefore, the total internal reflection takes place and the beam reflects back and it will move like this from the other surface. Similarly, the lower part of the beam will also strikes and it will introduces the angle of incidence 45 degree more than the critical angle, therefore, this will also reflects back. In this way, the letter A can be turned to 90 degree. Second one, we have under arrangement of the prism, which turns the incident beam of light to 180 degree. Here also the same total internal reflection phenomenon takes place. A beam of light enters into the prism, say it is as X, Y, Z. The incident beam strikes at X, Z at point P and Q. The angle of incidence here also 45 degree, which is more than the critical angle, that is why total internal reflection takes place. In this way, the incident beam of light is turned to 180 degree in the second arrangement of the prism and first arrangement of the prism, the beams turns to 90 degree. So, the first arrangement is used in periscopes and the second arrangement is used in binoculars. So, the principle on which these prisms are works is based on the total internal reflection. Next we will see the optical fibers. Optical fiber is a device which is based on the total internal reflection and it consists of 3 tubes. First one is called core, whose refractive index is 1.7 approximately. Second layer is said to be as cladding and its refractive index is 1.5, and the upper layer is called buffer coating, which is used to protect the inner layers. Here the lower core, whose refractive index is 1.7, act as a denser medium and it is surrounded by cladding whose refractive index is 1.5 and this will act as a rarer medium. So, the conditions for total internal reflections will satisfy here and the total internal reflection will take place at each and every point of the inner core. As a result of that, multiple total internal reflection will take place because of that light transfers from one end to another end. Here let us see the structure. We have the inner core whose refractive index is 1.7, mu is equal to 1.7 and the upper one is 1.5. When a beam of light enters here from the denser medium, now the beam of light has to pass through the rarer medium if it satisfies the condition of total internal reflection, that is whenever it strikes at the cladding surface, if it introduces an angle of incidence more than the critical angle, then the incident beam reflects back into the same denser medium of the core, and then here again the total internal reflection will take place. In this way, due to the total internal reflection, light will pass from one end to another end. So, buffer coating is actually used to protect the inner layers. It is made up of Teflon or some hard plastic, which is polyurethane. So, this is the working of optical fibers. These are actually bundles of tubes that is based on total internal reflection. Now, we will see some of the application of total internal reflection. It is used in telecommunication to pass the signals from one end to another end, because we know that light moves faster whose speed is 3 into 10 to the power 8. So, any signal that can be converted into light and that can be transmitted from one end to another end with the help of optical fibers very fastly. Second one, it is used in medical field, which is said to be as endoscopy, to see the inner structure of the body, such as inner stomach and then lungs, etc., to search whether any tumor or anything has happened at the interior part. Third, optical fibers can also be used as a decorative light. Next one is, it is also used in refractometers and it is also used in sensors. Next one is, it can be also used to transfer the two-dimensional pictures from one point to another point, and it is also used to pass the laser beams, and again it can also be used in internet communication systems, etc. So, these are some of the uses of optical fibers. Next, we will see the refraction through lenses. Here, while drawing the ray diagram for the case of refraction through the lenses, we must follow the law of refraction. We have two types of lenses, one is convex, another one is concave. Let us see the structure of convex lens. Here I have drawn the convex lens whose surface appears to be bulges outward. Now, for first surface AB, the radius lies on the right hand side, which is named here as R1. Similarly, for the surface BA, the radius lies towards left hand side, which is named here as R2, whereas C2 as well as C2 and X is named as the radius for the surface BA, and the radius YG is acting as the radius for the first surface BA. A principal axis is there which passes through the pole. Now, for the case of concave lens, it will concave inward. The radius for the first surface lies towards left hand side, whereas the radius R2 for the surface DC lies towards right hand side. So, these are the differences between two lenses, that is, for surface BA the radius lies towards left hand side, whereas for the surface DC the radius lies towards right hand side. Similarly, the radius for the second surface lies left hand side for convex lens, whereas for the surface AB the radius lies left hand side, and for DC the radius lies towards right hand side. Now, we will try to understand the ray diagrams for these two lenses. Now, we will see the ray diagram related to convex lens. Here in the first case, object is located at infinity. So, the rays which are coming from the infinity must meet at focus point. So, all the rays that are coming from the infinite point meets at focus point. So, here the image which appears to be as pointed image is pointed, formed on the right side of the central line, and it is real image. So, we have to remember that all the rays that comes from the infinity must meet at the focus. Next one, we are considering the situation when the object lies beyond C. Say, let us suppose that AB is the object which is lying beyond C. The parallel beam of light has to pass through the focus, as I told in first case. So, the parallel beam which arises from the object passes through the focus point. Another beam, we can take the beam which passes through the pole. Here the beam which passes through the pole do not bend. The two beams meets at a point, intersects at a point, and we get an image between focus and center. So, here we have B dash and A dash as the object. We are seeing that the image of the object is inverted and it is small compared to the object's height. Here you can take H1 as object height and H2 as image height. So, image is shorter than or the smaller than the object height. If the object lies beyond C, image will form between focus point as well as center, and its size is smaller than the object size. In this case, we are seeing image is inverted, real and small. So, magnification in this case, which is equal to m equal to h2 by h1 with negative sign, is equal to v divided by u with negative sign. Using sign convention here, v is positive, u is negative, minus minus becomes plus, here v divided by u, and the magnification in this case is lower than 1. So, m is less than 1, that is the size of the image is smaller than the size of the object. Next, we will see when the object is placed at center. So, when the object is placed at the center, we will get the same size on the other side, that is, if we take h1 as height of the object, we will get the image also as h1. Here magnification is m is equal to h2 by h1, which is equal to 1, that is the size of the image is equal to size of the object. Now, we can say that the object, when it is placed in at the center point, the height of the image will remain same as the height of the object, and similarly the distance at which the image is forms is also equal to the object distance. So, again image is inverted image we will get inverted real. In next case, object is placed between center and focus point. Here in this case, we get the image formation beyond C on the other side, and the size of the image is enlarged image, that is larger than the size of the object. We get enlarged image, enlarged, inverted and real. So, here in this case we get the image as enlarged, real and inverted, and the magnification here is given by h2 divided by h1, which is equal to v divided by u, or m is greater than 1. So, when the object is placed at a center, we get magnification is equal to 1. When the object is placed beyond C, we get magnification less than 1, and when the object is placed between C and X, we get image magnification is greater than 1. In all these cases, we are getting real inverted images. Now we will see the other situation where the object is placed between focus and pole. Here we have the object placed between focus and pole. We see that the parallel beam which arises from the object moves towards the focus, and when we extend the other ray which passes through the pole, when we extend both the rays, we are seeing that on the other side both the rays are moving apart, but on producing these two rays it meets on the left hand side, forming an virtual image. So here in this case we are getting a virtual image. So this situation is used for the case of microscope. Second one, the other case is when the object is placed at the focus, image will be formed at infinity. So there are two conjugates. When the object is placed at infinity, we get the image at focus, and when the object is placed at focus point, we get the image at infinity. These are the situations we saw on today, and we will see the remaining topics in our next class. Till then, I hope that you all will practice. Thank you.